Okay, today we're going to talk about the major themes of anatomy and physiology. And we already alluded to the difference between anatomy and physiology. We said that anatomy is the structure, while physiology is the function, and they are both intertwined and connected. They are inseparable. Anatomy gives us the function. Anatomy is what makes the function possible, and the function is not done without the structural support. So anatomy and physiology are complementary and they are never entirely separable. So physiology provides meaning to anatomy, and anatomy is what makes physiology possible. So when we examine the body, there are multiple ways, multiple methods in the physical examination. We have inspection, where we use observation to look whether the patient is in distress, whether the patient looks disheveled, whether the patient is in a state of coma, for example. So these observations we make help us make a decision for the better of health of the patient. Palpation is when you use the palm and when you use the feeling of the hands and your palms to feel the structures, and to feel the pulse and to feel if there is to detect the heart rate, for example, on the pulse rate. Auscultation is when we use a stethoscope to listen to sounds produced by the body, such as the apex beat and such as the to detect if there is any abnormal sounds in the lung, such as any tactile vocal fremitus or any dullness and so on. Percussion is a form of examination also where we put our um, fingers on the body and then we feel the resistance and then we trigger a sensation and detect or listen to any emitted sound and abnormalities. This is not used anymore. So percussion was you would put your finger like that and tap on it and then feel a sensation. That would give you a sensation if the patient has any form of splenomegaly, if the spleen is abnormally enlarged, or if the liver is abnormally enlarged, hepatomegaly or splenomegaly. But that is not done anymore. This was in the past. So this could be done maybe in a brief physical examination to confirm that the patient needs to be sent for diagnostics. But what we need to do is to send the patient for ultrasound. So when we send the patient for ultrasound, we can detect that there is an increase in the spleen or the liver, for example. Dissection is when we cut and separate the human body tissues to reveal if there are any relationship between the tissues. So a cadaver is now used for that. As we said in the past, they began performing these types of unethical experiments on slaves, on prisoners. But then they had an awakening and they said that's unethical, so don't do it to human beings altogether, whether alive or dead. Then they started doing it on animals. Then they started to draw conclusions that the liver of the human being may resemble the liver of the monkey with that looks sometimes like a finger projections, and that was entirely wrong. So then they resorted to cadavers. There's comparative anatomy, and that is when we study and dissect multiple species to learn about them. So we've learned that we are more closely related to the chimpanzees, the monkeys, than the gorillas. So the monkey has more in common with us than the monkey has in common with the gorilla. So many people have the misunderstanding that you know um, evolution means that we evolved from monkeys. That our origin was a monkey, which is not true. It's not a situation where you have family photo album and they tell you that's your father, that's your grandfather. Who's that monkey? That's the great grandfather. It doesn't work that way. So it means that we are lineage, side lineage. There is some in common, and that's actually very good. Why is that good? Because we can use monkeys as animal models for medications. So most of the medications, and but that's the most expensive model. I mean, but it's the most closest thing you can get to simulating that medication on a human being. There's also exploratory surgery, and that is when, oh, back in the day, they had no diagnostics, no ability to do X-rays or to do a CT scan or MRI. So they used to open you up to see what's inside you, see what's wrong, just to explore, to find out what's inside your belly. And that's not good. So now we resort to radiology. So things are more advanced. So anatomy, there's different types of anatomy. There is gross anatomy, where we study the macro structure and things that are seen with the naked eye that we do not need a microscope for. And then there is histology, which is the microscopic anatomy. You look at really small tissues. And then there is histopathology, and that is when you look at disease tissue and you look at the development of the mechanisms of disease formation. There's also cytology. Cytology is when you study the structure and the function of the cells in fine detail. So we talked about how the cell is the unit of health and the unit of disease. We are healthy because our cells are healthy. We are sick because our cells are sick. We are alive because our cells are alive. And we are dead when our cells are dead. Okay, so this is now known as the deconstructionist school of thought. Back in the day, they used to look at the human being as a whole piece and look at it holistically. But then they realized that's not that's not the case. As we mentioned earlier, we begin with stress, cell injury, cell death, cell necrosis, then progresses on to tissue. So the cell is the foundation. Many people have, they think that the basic thing, like for example, if you look at the pyramid, what is the most important part? Do you think it is the base, or do you think it is the apex, the top? It is the base. Because if the base falls, that's what makes the whole pyramid crash down. So we talked about a tree that is very strong to survive the hurricane. It has to have really deep, deep branches. So your base, that's why this course, anatomy and physiology, is the base. That's what you begin with, because you build up on it. If your anatomy and physiology is weak, I mean, everything that comes on top of it is going to crash down. So this is going to require you to invest a lot to understand. So now the cell, they found out that the cells together, they give us the tissue, and many tissues give us the organs, and many organs give us organ systems, and many organ systems give us organisms, and many organisms give us population. Then they realize there is an imaginary base even below the base, and that is the building block of the cell. So the cells are made up of atoms, they are made up of molecules, and they are made up of organelles. The mitochondria and your Golgi body, the cytoplasm and the plasma membrane and the ribosome and the endoplasmic reticulum and so on. So they realized that even though on their own, these building blocks of the cell on their own, they are useless. They cannot perform anything. But together, they make my cell functioning. So when I study the endoplasmic reticulum, when I study the Golgi body, when I study the ribosome, I can do something about it when the cell is sick. Because when the cell gets sick, what gets sick about the cell? It's one of these guys. Something wrong with the atoms, something wrong with the molecule, something wrong with an enzyme inside the cell. That's what happens with cancer. So these receptors, the receptor molecules, these are enzymes. So the receptors are malignantly activated, leading to excessive entry into the cell cycle. So I mean, if we just study the cell holistically, that's not going to help. But when we dive into the cell, studying these molecules then we can find and devise some pharmacological intervention that helps us repair that wrong thing with the atom, wrong thing with the molecule, that's something that's wrong with the ribosome, or how to hijack the DNA into transcribing proteins that help us. So now they are starting to lean towards cytology, which is looking at the basic structure. So now, but there's nothing below that. You can never go below the atom. I mean, this imaginary line, that's the least you can go. So now they are doing the research there. So here is where the problem, but that's the foundation. So they are looking more into the cytology. Okay, that's anatomy. What about physiology? Physiology is now divided into multiple disciplines, multiple schools of thought. You have neurophysiology, and that is the physiology of the nervous system. When you are just focused and concentrated on the nervous system, we're going to be doing neuroanatomy and neurophysiology in this course. And then there is endocrinology, and that is the physiology of the hormones. And we alluded to that. We talked about how calcitonin is used for negative feedback when there is hypercalcemia or hypocalcemia. When there is, which of both? Do we use calcitonin when there is hypercalcemia or hypocalcemia? When there is hypercalcemia, we use calcitonin to start taking calcium from the blood and dump it on the bone. Very good. When the opposite, when there is hypocalcemia and we are depleted of calcium, we have too little when there is too much calcium, why is it dangerous and why do we need calcitonin to remove as much calcium as possible from the blood and dump it into the bone mountain? Why can't we just leave it there and we have a lot of calcium in the blood? Why is that dangerous? It can affect your heart. If there is too much calcium, it can affect your heart. How? It builds up. It builds up like it clogs the heart, calcification. That's a good one. I didn't teach you that one, but it's true. It doesn't build up it builds up on the valve. Very good. It builds up on the valve. It makes the valve really sticky. They cannot open, so blood cannot pass through. That's good. It's called metastatic calcification. Okay, so that's I'm sorry, that's called dystrophic calcification, but it's a form of calcification. But that's not what I said there. What did I say there about with too much calcium? When I said that when there's too much calcium, why is that bad? I said when there's too little calcium, calcium is important for the action potential, for the depolarization, for the electrical stimulation. But when there is not enough calcium, we cannot mediate that depolarization and that membrane potential, so the heart cannot beat. So that's for too little calcium, hypocalcemia. Too much calcium. Why is hypercalcemia dangerous? Besides calcification. Very good. She just derived it. I didn't even say it. I didn't even mention it last time. Very good. What else? Remember what I said about on to off? If too much calcium is like a key in the ignition, it turns what on? Calcium, if too much calcium, is going to turn on something. Very good. Which enzymes? Good. The auto. I'm squeezing every bit of knowledge. Okay, so it's gonna turn on off to on what enzymes? Autocatalytic enzymes that destroy the pancreas, leading to pancreatitis. So now the pancreas is supposed to secrete this enzyme to degrade food. Now there's no food, but there's calcium. It's gonna turn it on. So now these enzymes are gonna destroy. The osteoclast is the bone. They're gonna go and destroy the bone. Very good, but that's for the bone. This is the pancreas. So they are known as trypsin, and chymotrypsin. These guys, they're gonna go destroy the pancreas that is holding them. Okay. Pathophysiology is when you study the mechanisms of disease, how disease forms. That's my favorite branch of physiology. And then there's comparative physiology. It's when you study different species to learn about the body functions. And that's the basis for much of our understanding of human physiology and the development of new drugs. Because we don't test on human beings, we test on animals. And then we try to simulate it on the body of the or a human being. Okay, so now we're gonna go into the history. This is one of your classmates earlier today told me it's Hippocrates. That's how you say the name. I was calling him hypocrites all the time. The poor guy. He was not a hypocrite. He was a good guy because he was the first one to tell the people a disease. We should look for the natural causes of disease, for the scientific causes of the disease, so we can find medication. We should stop saying you're sick because the demons, because the gods are up there and the monster and all of that kind of stuff. That has to be, that has to end, and we should find testable, falsifiable hypothesis through experimental design to measure these measurable, testable hypotheses, so we can find and understand the disease. Although that stuff is not entirely wrong. That, I mean, I believe if you walk into a haunted house and come out, you're more likely gonna get sick or something like that. Or if you go to the beach in the winter where nobody's there and you just stay a night over there and you come back, okay, something bad may happen to you. That's, I believe in that kind of stuff. But it's up to you. You don't have to believe in it. But I do believe that sometimes there are unexplained, unscientifically proven causes of disease. You know, they ran an experiment where there are patients who were given placebo, and they were told that this is the cure for your disease, and they were cured. And some of them even developed side effects. So there are very mysterious things with how the human psyche and the human mind works. But just remember that Hippocrates was the one who actually originated the idea that we should just put everything into science instead of attributing it to superstition and myth and mythology. Then Aristotle came, and he believed that there's supernatural or physical causes. Like I told you, like that kind of stuff is not scientific, but it is not completely ruled out. There are some like really weird things out there that lead to you being sick, aside from those testable things like infectious diseases and physically. Do you see what I'm trying? You get what I'm trying to say? Yeah. So there are things that are causes of the disease that are not entirely scientific, but we do what we can, and we try to whatever that we can deconstruct down to the scientific world and test. We can do that, and the rest of the stuff, I mean, we cannot do anything about it. Okay, then there was the first female doctor, and that was Metrodora, and she was a doctor back in the day. Females could only become doctors of obstetrics and gynecology. So she published her very first medical textbook, and it was about the diseases of the women and um, obstetrics and gynecology. Then there was Claudius Galen, and he was the doctor of the gladiators. I mean, when they fight and they punch each other in the face, and he would go and treat them and take a little bit of the pus from this guy's face, a little bit of blood, and then he studied that, and actually he came up with very interesting things that started off as hypothesis and prediction. And he put in his book very interesting things that were later on used in the in the scientific world as a as a encyclopedia. Then there's Maimonides and Avicenna. Maimonides thrived during the time of the Jewish world. So back in the day in Christendom, there was a, a whole declaration that science is separate from the state, is separate from the church, and there shouldn't be scientific experiments done on the bodies of the people and so on. This was not happening in the Jewish world and in the Muslim world. So those two scientists, Maimonides was Jewish and Avicenna was Muslim, and both of them, they did their experiments, and everything was also used in this progression of science to become what it is today. So they were all very important contributions. Okay, so these are the more modern. These are the more modern scientists. You have Andreas Vesalius, and he was uh, when they relaxed the restrictions on the dissection of the cadavers, he performed his own dissections, and he back in the day, the scientists used to sit in a chair known as the cathedra, and then the barber surgeons, they would be dissecting, because back in the day they didn't have embalming and they did not have preservation, so you actually had the actual body, so it was stinking, smelling really bad. So the scientists used to sit really far in the back and send these barber surgeons to just do all the dissection and deal with the smell and the putrefying. And but he actually went in there and he dissected himself, um, these cadavers. And later on, they developed how to preserve the bodies and to embalm and remove all of that stuff. Okay, William Harvey. William Harvey, we're going to learn more about him in anatomy, physiology too, and that he had very important experiment for the hemodynamics and the movement of blood. And he discovered that the blood vessel is not just the empty tube through which blood goes. There are valves in there. So that's how varicose vein develops. So for people who have professions of standing for too long, like professors or teachers or police officers, guards, or pregnant mothers, and also obese patients. So what happens is the blood is trying to go up against gravity, and there are these valves that are not supposed to reflux. They are supposed to be one-way valves to allow blood to move up. And if blood wants to fall backward, it prevents it because it only opens in one direction up. When it want to fall back, it's going to close. It's not going to allow it back. But when these valves defect due to obesity or standing for too long and damage to the blood vessels, what happens is blood starts to fall against the direction and reflux, and that leads to the pooling of the blood and the engorgement of the blood vessels. Okay, Galileo was a physicist who was preoccupied with telescopes and learning about the stars, but his idea was used to develop the telescope to study the microscope. So he discovered that if you use an ocular lens close to your eye and a lens that is close to the object, these two can help you magnify. But he had a huge telescope for the skies. Then they made a microscope that is with the same idea, but it's too small. And then they used his idea and developed the microscope over the years. And then Robert Hooke came to bring his first microscope. And then Anthony van Leeuwenhoek, he's the one who actually pioneered the work with microscopes for many years and published a lot with it. Okay. Then came the beginning of the cell theory. I mean, what is the cell? So all organisms, we said that cells give us tissue, tissue give us organs, organs give us organ systems lead to organisms, and many organisms give us population. So he put the first tenets of the cell theory, what he considered to be perhaps the most important breakthrough in the biomedical history, and all functions of the body are interpreted as effects of cellular activity. So he discovered that only come from cells only come from I'm sorry, I did not hear anything. What from living organisms? Very close, but do they come from organisms? So cells come from other cells. Very good. From other cells. So if you don't have a cell, so if you bring an organelle from one cell, cytoplasm from another cell membrane from another cell, the ribosome from another cell, you combine all of them together. Now, can you have a living cell, a functioning cell? No, you cannot. But the cell can come through mitosis from cells that came before it. So we talked about healing. So in healing, after inflammation, if the tissue that was harmed is a regenerative tissue, we have different kinds of tissue. We have tissues that are terminally differentiated. They cannot differentiate any longer. They cannot proliferate anymore. So when they are damaged for life. You don't get any replacement, and you just get scar tissue deposition. And other tissue, like epithelial tissue in your skin, I mean, the more you lose, you can regenerate real quickly. So that regenerative tissue shows you that the cells have come from other cells before them. So the old cells were scraped out, and the necrotic tissue was removed, and new cells have built up. Okay? Okay, so there are advances in different fields where they talk about the germ theory of diseases, and that these germs, these infectious organisms, the bacteria, they secrete endotoxin, exotoxin, and that damages the cell membrane, breaking the integrity of the cell structure, and all the intracellular content of the cell spills out. So the cytoplasm is full of many proteolytic enzymes, many degradative enzymes. These are dangerous. So when they spill out, they start destroying nearby tissue. And there are mechanisms of heredity. So there's autosomal diseases. There are sex-linked diseases. There are dominant genes. There are recessive genes. And then they learned about the structure of the DNA. We talked today about the central. What did we learn about? The central dogma of biology. So what does the central dogma of biology say? To proteins, very good. So DNA to mRNA is through transcription. So don't forget that part. That's part of the central dogma as well. And from the translation. Very good. Okay. There's advances in medical imaging. So now no need to open up the stomachs, no need to open up the abdomen of the patient just to see how the liver is. Is it too big or too small? I mean that's here the risk outweighs the benefit because they're real dangerous. Scientific method. Scientific method is the process of performing science, including careful observation, logical thinking, and proper analysis of observations and conclusions. There's science and scientific methods that set the standards for truth. So now we need to have to learn that our hypothesis that we are about to test. If we need to make an experiment, we have to find out the independent variable and then the dependent variable, and both of them are testable. I cannot be testing, what is the level of love or the level of hate or that kind of stuff, type of stuff that cannot be tested. Although emotions are tested in the sense of hormones. So there's dopamine hormone, there's a stress hormone, and so on and so forth. So there's an inductive method, and that method is reliant on many observations that lead to predictions. So you observe many things happening. You see a goat. The goat is eating from one grass and then it starts jumping all night long. Then you start to make a prediction that if those goats, this is what the shepherd have discovered, coffee. That's how they discovered coffee. They saw that their goats, they eat from that grass and they start jumping all night long. So they didn't know what was that. Then they discovered that was coffee. So that's an example of inductive method where you make an observation and then based on that you make a prediction. Okay, there's the hypothetical deductive method, and that is where we have a hypothesis. A hypothesis we make, if this, then that happens. But this hypothesis has to be falsifiable. What does that mean? That means if I make a medication and call it medication X, and this medication is supposed to make the patient, is an analgesic medication, meaning that it makes the pain sensation less. So the patient is not going to be in pain when they take the medication. So I have two groups, both of them in pain. I give the first group my medication X, and I give the second group a capsule full of water, and both of them take it. If the group that took the medications, pain went down, it's because of the medication. And if the other group, pain did not go down, it makes sense that my medication is effective. But if I only give one group, if I only give one group who is in pain my medication, I have no, then I cannot falsify that. I cannot say that maybe, they can tell me, who knows, maybe their pain went down not because of your medication, because of something else. But when I have another group who haven't had my medication and their pain didn't go down, but the group that took my medication's pain went down, now that makes sense. It makes sense that my medication is effective. So we need to be able to falsify the hypothesis and prove that it's not just one way, that the other way is not possible. So I don't just prove that I have one way of solving the problem. I must prove that the other ways are also ineffective. That's how you're able to develop your uh, a prediction. Okay, sample size. Sample size is the number of subjects in a study. So, I mean, if they tell you there's a medication that was tested on a sample size of 100 patients and another medication that was sampled on a sample size of 1,000 patients, which one is better? 1,000. So that shows there is higher reliability and high validity. There's a control group. A control group resembles the treatment group, but they do not receive treatment. They receive useless things that will not, definitely not affect the outcome. Psychosomatic effects. Psychosomatic effects are effects of subject state of mind on her or his physiology. It's tested by giving a placebo. Then there's also experimental bias. So experimental bias is a problem where the experimenter is so eager to get results, they end up interfering with the experiment, not knowing. So for example, let's say I'm running an experiment on you guys passing the course, and you taking the exam, I'm walking around, hey, the answer is C. Hey, because now I have a vested interest to make sure to get results that you guys pass. So I end up telling you what the answer is. So now that is solved in the experiment by a double blind method, where the researcher doesn't know which group is controlled and which group is which group is control placebo, which group is the experimental group receiving the actual medication, and the two groups themselves, they don't know which part of the group am I. Am I receiving the placebo or am I receiving the actual medication? So now we get actual results. But if they know, then that's gonna interfere. It's gonna lead to bias. So the patient knows that they are receiving placebo, they're gonna say, "Oh, it's not gonna have any effects on me." But you just tell them you don't know. Just take the medication, and it could be either or. We will not tell you which group you're in. Statistical testing. Now, why is statistical testing important? It's important for significance. So let's say I have a medication. The medication brought down my pain from 100% to 98%. Another medication brought down my pain from 100% to 50%. Another medication brought down my pain from 100% to 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 10%. To 10%. I mean, which one is is the most significant? It dropped it down to 10%. I mean, this 98% is insignificant. I mean, that's nothing. That's 0.2%. I mean, that's 2%. That's really not even worth the money I spent or the time or the effort. So that's why statistics are very important, because they teach us how significant the results are. So peer review are very important, because that's how you get counsel from your associates, from your colleagues. So if you want a grant to run an experiment, so you give it to your colleague will say that experiment has already been done before, or maybe I think you could hit two birds with one stone. So while you're testing this, test that at the same time, and maybe you can change your setting a little bit. So it's very important to have counsel. You have counsel from the experts. You don't have counsel from somebody on Facebook or on the social media telling you, listen, you want to lose weight? I tell you how. It's the peppermint plus the nonsense. You put them together, and then you're gonna lose weight, and that's the cure for cancer. These people, they are not experts, but who you should listen to is the experts. And actually, the more experts you listen to, so don't just confine yourself to one expert. The more experts you get their counsel, the better. So you should not rely on your intelligence, because intelligence is deceiving. You should not rely on the counsel from people who are inexperienced or people who have no expertise. You should base your decision on the counsel of the experts, even if it goes against what you in the end, it's your decision, but you should always tilt to follow the guidance and the counsel of the experts. Okay. Okay, so a scientific fact, what is the difference between a fact, law, and a theory? So the law is usually describing one thing, while the theory is describing multiple things. And the most important theory we talked about is this evolution, the theory of evolution, that, we evolved from a common ancestor and we continue to change under the pressure of stresses so we can adapt. So, if people are with a certain population, and the evolution happens at the level of the population, so it takes like thousands of years, like hundreds of thousands of years, millions of years. But you cannot say something evolved overnight. So the population who lives on the top of the mountain, living on the top of the mountain, they there is less oxygen up there. So what happens is their body responds by generating more red blood cells. So more red blood cells, more hemoglobin. So that will tend to them getting more oxygen saturation into their blood. Okay, so this is Charles Darwin. He's the biggest influential biologist, and he presented a well-supported theory of how evolution works. And he says that species originate and they change through time, and they help understand the human body. So evolution is a change in the genetic composition of a population of organisms, and the development of bacteria resistant to antibiotics. So if you had 100 bacteria and you take an antibiotic vancomycin, and vancomycin will kill 98%. The 2% who resisted, in the next cycle, they're going to rebirth and they're going to have multiple bacteria. That bacteria will survive. The 2%, when they build up to become 100%, when you give them vancomycin again, it's not going to kill them. So that shows you that there is a resistance. So selection pressures, these are forces that promote reproductive success of some individuals over others. So predators who are stronger, who are faster, they tend to survive. And the deer who run faster than others are able to survive because they are more fit, while the ones who fall, they will be eaten by the tigers and the hyena and the lions. Okay, adaptations. Inherited features of anatomy and physiology that evolved in response to pressures and that enable the organism to succeed. An example is the better camouflage. Okay, so some lizards develop the ability to camouflage excellently with the trees, and that led to their survival of predator attack. So primates were arboreal. What does arboreal mean? So some human anatomical and physiological features can be traced back to ancestral primates. So arboreal meaning you live at the top of the tree. So to escape, so that's how you're going to be the safest when you are living at the top of the tree. You are away from these dangerous predators, the lions and the tigers and so on. They we also because we were arboreal, we had very strong shoulders, so can be able to jump from one tree branch to the other. And there are opposable thumbs and prehensile hands, and they grasp the branches and manipulate the objects. So the thumb is the most important part of your hand. If the thumb is cut off, using these four fingers is very difficult. They are useful only when they are used with the thumb. So all of these guys represent like 20%. The 80% is actually the thumb. It's what gives us the power. Okay, so forward facing eyes. So now our eyes structure are not like the animals that they are on the back or on the side. They are forward in the front because that gives us better access and better view. So we have better lateral view and we have better peripheral vision and we have better central vision. Okay, bipedalism is the ability to stand up and walk on two legs. So human beings were hypothesized in the past that we were not bipedal. We wouldn't walk on 2 feet like we do now. We used to walk on four. But now, millions of years have passed by, and now we're able, because we lived in the savannah, we're able now to walk on 2 feet because the selection pressures led us to be able to stand up and walk the uh, through the savannah. So that shows you how many millions of years ago what happened. So bipedal primates appeared, and then taller and larger brain volume and tool making generation appeared. Then after them, there was a migration to Africa, and then that just shows you that evolutionary medicines trace some of our diseases to differences between modern and prehistoric environment. What does that mean? That means that back in the day, sunset, everybody asleep. When I say back in the day, I'm talking about thousands of years ago. There was no artificial lighting. You cannot 11 p.m. now can sometimes look like 11 noon or 12 noon because the light is all over and people are working overnight shift. Back in the day, do you think the caveman had an overnight shift? So if caveman was knocked out at 7 p.m. or 8 p.m., but very healthy lifestyle, waking up in the morning, and but now people they sleep through the day and work through the night, so on. So that's the part of the study that looks at the differences, looking at the differences of evolutionary times and the changes that happen now, and how does that lead to some diseases. So now the cars that are in industrial New York City and all of this fumigation and all of these type of um, the gases that are emitted by the cars. I mean, it's all over the air. Even if you don't see it, that's what leads to so many respiratory system diseases. But if you go to like rural countries or poor countries, they live in really healthy natural environments with not, with no asbestos or with no smoke and with no car uh, emissions and all of that. Okay, so we talked about this. This is the hierarchy. That is the hierarchy of the complexity. That's the hierarchy of the complexity. And we said that we begin with molecules and atoms at the base, and then we have organelles. The organelles give us the cells, cells give us tissues, and then tissues give us organs, and then organs give us organ systems, and the organ systems give us the organism, and multiple organisms give us a population. So we mentioned that. So do you see now? Okay, so do you see now the atoms give us the molecules give us macromolecules, then organelles, then cells, and cells together aggregate to give us a tissue give us an organ, multiple organs connected together give us an organ system, and the organ system give us an organism. So sometimes one organ can have multiple different tissues. So for example, the skin, it can have nerve tissue in the skin, it can have epithelial tissue in the skin, it can have hair follicle in the skin. So that shows you we have multiple types of tissues. So the organism is a single complete individual. So the organ system is a group of organs with a unique collective function, for example, the circulation, respiration, and digestion. The organ is a structure composed of two or more tissue types that work together. We talked about that. The tissue is similar cells and cell products forming a discrete region of an organ and performs a specific function. We talked about all this. Okay, so we alluded to what reductionism was. So reductionism is when we deconstruct the human being holistically into the smaller parts that make it, and we study that. So it's a theory that large, complex systems can be understood by studying their simpler components. It's essential to the scientific thinking, but some properties cannot be predicted from individual parts. There's holism. Holism is when we look at emergent properties and they occur as we ascend the level of organization, and these cannot be predicted from the levels of individual parts alone. So humans are more than the sum of their parts. Okay, there is anatomical variation. So even the identical twins, they are not the same. They do not look, even though they look alike, but they are not identical by the sense of the word. You know, the anatomy and physiology that we're doing today, here and now, that represents the majority of the people. So normally the kidney is supposed to look like that, but it does not mean some people don't have pelvic kidney. Some people have a kidney that's in the pelvis. Some people have horseshoe kidney and that their kidneys are attached together. Some people have a normal aorta that looks like that, but now look at these three different types of aortas. They have variations in the branching of these aortas. So do not think that this anatomy and physiology is absolute to every single human being out there. There are some variations, very small variation. So we talked about negative feedback. And we gave an example of it. And so now life is a collection. Life is a collection of properties that distinguish the living from the non-living things. So we cannot have a clear-cut definition of what life is, but we can define life as it is we define life as an organization, in terms of organization, that the living things exhibit a higher level of organization than non-living things. And cellular composition, so the living matter is always compartmentalized into one or more cells. And we learned that metabolism is the sum of internal chemical change. And so metabolism can be divided into catabolism, which is the breakdown of macromolecules into micromolecules. So we begin with, for example, lactose. So lactose is the sugar of milk. It is made up from glucose and galactose. So what we do in catabolism, we cleave this bond. We break that, and we have glucose by one side and galactose. There is another enzyme that converts it from galactose into glucose, because glucose is what is shuttled into the glycolysis pathway. Okay, maltose, the sugar of oatmeal, is made up of glucose and glucose. And sucrose is made up of glucose and fructose. So glucose is shuttled into the glycolytic pathway, while fructose is converted by another enzyme from fructose into glucose. Then it's able to be put into the glycolytic pathway. But in the end, we break down from big molecules, from big macromolecules, from disaccharides, two sugars, disaccharides into monosaccharides. We break down from proteins into amino acids. We break down from lipids into glycerol and triacylglycerides. These are the process of breaking things down liberates energy and gives us ATP. The opposite is true. So remember when we were talking about glycemia, when we had hypoglycemia, we started to add, we started to secrete glucagon. Glucagon causes sugar to be deposited from the liver into the blood. Is that an example of catabolism or anabolism, build up? Was that an example of breaking down sugar or breaking down molecules from macromolecule into micromolecule, or is it an example of building up from micromolecule to macromolecule? So catabolism is when we break down from macro molecule, from big molecule into smaller molecules to get energy. That's catabolism. In anabolism, what we do is we build up from anabolism up to and that costs energy. So when we had a drop in sugar in the blood and we solved that by secreting glucagon, and then we added sugar into the blood, was that an example of catabolism or anabolism? Anabolism. So anabolism, we build up. So did we build up sugar or did we break down sugar from glycogen? Because remember, we said the liver was a store of sugar belts. Remember? Glycogen. So when we needed glycogen, we broke that down. We broke glycogen into glucoses, and then we liberated glucose into the blood. So we broke down glycogen into glucose. So that's catabolism. The opposite, when I had too much sugar in the blood and I used insulin, then we took all of the sugar in the blood and we built it up. We made it into the liver. So that's an example of anabolism. Excellent. So responsiveness, that's excitability, is the ability to sense, react to changes in the environment. We talked about that. Sensation, there are thermal receptors that feel if there is a sensation of heat. There's a sensation of heat and the ability to sense and react to changes in the environment. And they feel that there is heat, or they feel if there is extra salt or extra, these are called chemical receptors. They taste the blood. Does it have extra calcium? Does it have extra sodium? Does it have hyper sodium, known as hypernatremia, or too little sodium, hyponatremia, and then they repair that problem. So we always have sensors and receptors. There's mechanoreceptors, like when the baby is suckling the breast milk of the mom. So these mechanoreceptors, when they are stimulated, they send, there is mechanical sensation, and that causes the secretion of oxytocin, which does what? Oxytocin? When the baby is suckling, that causes oxytocin to be secreted. What? Yeah, produce more milk from the milk ducts. Very good. Movement. So another characteristic of the life is now the living objects are organ. So this compares for us the difference between the living and the dead. The living are more organized. The living have a cellular composition. The living can do metabolism, catabolism, or anabolism. The living can respond to stimulation and the movement, and the living can move from one location to the other, while the dead cannot. Okay. Characteristics of life. So there's homeostasis. We talked about that, and how to restore, to maintain that is constant. So many people, so your understanding of what homeostasis is very important. Homeostasis is to activate all the different systems in your body to ensure that you have a constant internal environment. Outside could be very cold, outside could be very hot, but inside must be within homeostasis. So outside could be 37 39 degrees Celsius. That's too hot, hyperthermia. Outside could be 30 degrees Celsius. That's too cold. But inside must always remain at 35 degrees Celsius, known as constant internal state, known as homeostasis. So we do shivering thermogenesis to return to homeostasis, and we do sweating to return homeostasis. So outside, we're not concerned with outside. We are concerned with ensuring that there is a constant internal environment. Development. So homeostasis, maintaining relatively stable internal homeostatic conditions. Development is a change in the form or function over time. So differentiation is the transformation of unspecialized cells into cells with a committed task. Okay. Growth. So growth is an increase in the size, and it occurs through the chemical change. Reproduction. So organisms produce copies of themselves that pass genes to the offspring. And the evolution. So sometimes there is a genetic mutation that causes a problem, like in sickle cell anemia. Sickle cell anemia, there is a defect, there's a mutation that causes a problem with the structure of hemoglobin. So now hemoglobin can never accept oxygen and deliver it to the tissue, and then unload to the tissue the oxygen, and then uptake the carbon dioxide and return it back to the lungs. So that shows you a problem where mutation can be bad. Sometimes mutations can be good. You know, some people, so that same mutation of sickle cell anemia can give you resistance against malaria. So malaria can never invade a hemoglobin that is sickle cell. It can only invade hemoglobin that is biconcave, that is normal structure. Sometimes they also discovered that some people can never get HIV because in order for HIV to happen, it must bind to the outside layer. So, like let's say this is the white blood cell that must be infected by the virus. So, in order for the virus to be internalized inside, so in order for the virus to be internalized inside, it must first bind on the outside. There is a receptor and there is another side receptor here. So the virus comes and it binds to this side receptor. Some people have a mutation. This side receptor is non-existent. So the HIV virus can never be internalized due to their mutation and the loss of this side receptor. Physiology is even more variable than anatomy. So there are variations in sex, age, and diet. So when we give numbers like what is the normal blood pressure? Is 120 over 80. That number is for who? It's usually for a male who's 22 years old, who is 154 pounds, and who performs light physical activity, consuming 2,800 kilocalories a day. We're not talking, so for example, if we go up to a male who is 70 years old, obviously these dimensions are going to change. So we have to take into account there are sex specific variations, there are age specific variations, there are diet and weight and physical activity, genetics and environment. So these different factors, we have to take them into account. So the failure to consider variation can lead to over medications of the elderly. So you do not give the same dose of medication to a young, healthy man that you would give to somebody who's suffering from the same disease and is a baby, pediatric. So I have bronchitis, and a baby who's 2 years old having bronchitis, and a grandmother who is 92 having bronchitis. Are we going to have the same dose? So not. So we take into account the sex, the age, the weight, the diet, and all of that. Okay. We talked about negative feedback and positive feedback. I remember back when I was in college, my professor gave us an excellent example of to test our understanding of negative and positive feedback. He said that back in the day they used to have electric blankets. And electric blankets, they used to have two remote controllers on each side. So he said him and his wife were laying in bed with this big electric blanket that is divided into two pieces. And a mistake happened. So they switched they switched their controllers, their electric blanket controllers. So he said he felt a little bit cold. So he took the controller and he increased the temperature a little bit. But whose side does the controller that he's having control? It's his wife. So now who's getting more warm? It's his wife. So now his wife says, "Oh my God, it's getting warm in here." So she takes the remote controller and she makes it a little bit colder. But who does that affect? Him, who was what at the beginning? He was cold in the beginning, and now she's making him colder. And now he feels a little bit cold. It's like, oh my God, it's getting cold. Let me make it more hot. And she's more hot. So she keeps making him more cold, and he keeps making her more hot. So he asked us, that's an example of a negative feedback or a positive feedback. Raise your hand if you think that's an example of a negative feedback. Okay, raise your hand if you think that's an example of a positive feedback. Some people didn't raise their hand either, and either way. Okay, I thought it was negative feedback, and I was wrong. It was positive. Because how do you tell? Remember with the baby, the more the baby push, the more the baby is pushed out, right? So you look, if you want to tell if something is positive feedback or negative feedback, you compare the stimulus to the outcome. So the baby's stimulus was to push the cervix. What was the outcome? Him being pushed more. The stimulus was him suckling the nipple to get milk. Now he got even more milk. So that's an example of things getting more and like the outcome amplifying. So he was cold. Even though he was intending to make himself warm, what happened was he got even more cold. So that's positive feedback. So the stimulus he did led to exacerbation of the symptom. She was hot. She did something, it doesn't matter. She was trying to do what? That's not what it matters. What matters is what did it lead to? So that's how we tell the difference between positive and negative feedback. In hyperglycemia, insulin does negative feedback, reduces glucose. In hypoglycemia, glucagon does negative feedback and increases blood sugar concentration.
Why is that? Because it's feeding off.
I'm sorry?
Why is that? Because it's feeding off.
So the negative feedback is when we are reversing the stimulus. So the stimulus was hyperglycemia. We had too much sugar. That's the stressful stimulus. So stimulus is not always a good thing. So here the stimulus was a stressful hyper. Remember, we don't want hyper or hypo. We want U. So here we don't have euglycemia. We have hyperglycemia. So how can I repair hyperglycemia? By doing more positive feedback or by negative feedback? Negative feedback. So we secrete insulin to bring down the, okay? Okay, sure. No, because we said when hypo, we go up to hyper. So negative means you are the opposite of the initial stimulus. So when you had hyperglycemia and restored it back by doing hypo, that's negative feedback. So you went the other way. You went up to hyperglycemia and the integration led to drop of sugar. So these are two opposite directions. That's negative feedback. It could be the other way around. You could have a drop in blood sugar and you secrete glucagon to increase blood sugar. Both are reversed. So the initial stimulus and the response, if they are in opposite directions, that's negative feedback. It doesn't mean always increase or always decrease. They just have to be the opposite. Yes?
So can you say like negative feedback is bringing it normal and the positive feedback is
Positive feedback is when you intensify. So,
like, yeah,
yeah. So Yeah, positive feedback is when you intensify. If it's too low, you make it lower. That's positive feedback. So, for example, a patient who has a drop in blood sugar, if you give them insulin, that's positive feedback. You give them an insulin injection by mistake. It happens in the emergency room. The patient has hypoglycemia. You give them an injection of insulin. They have even more hypoglycemia. Is that negative feedback or positive feedback? That's positive feedback. If a patient has too much sugar, you give them by mistake an injection of glucagon. That's even more hyper. So now you went from grade 1 hyperglycemia to grade 3 or 4. But when you had hyperglycemia and you gave insulin and you went down to euglycemia, that's negative. And it could work the other way. If you had hypoglycemia and then you inject with glucagon and you go up to euglycemia, that's negative, yeah, because they are in working in different direction. But if you go, yes, sepsis. So what happens in sepsis? What happens in sepsis? What happens in sepsis is you have an infection in the blood. The infection in the blood triggers a state of inflammation. Inflammation means the blood vessels are going to widen. Why? Because remember we said in inflammation we have five signs: redness, heat, pain, swelling. So how do we get redness? It's because the blood vessels are dilating to send a lot of blood there, and because the blood has the white blood cells, the cups. So you want to send, there is infection there. So you want to send as many white blood cells, neutrophils, eosinophils, basophils, lymphocytes, macrophages. You want to send them to the site so they can fight the infection. So it makes sense that we don't constrict, make the highway tighter, we make it wider. Now the problem is when this inflammation is there for a short amount of time, that's okay. But when it is there for a long amount of time, what does that do? That drops blood pressure.
But
So,
I'm saying like the end of chest, so like when it's organ death, like the organs are shutting down, would that be a positive feedback?
so what happens? You do not die of the feedback. You die because the blood pressure deteriorates. So yeah, it could be a form of positive feedback. So a positive feedback where blood pressure drops and keeps on dropping and keeps on dropping. Yeah.
That would be.
Yeah, that would be. Okay. All right. Any other questions? So this concept is very important. And we said that vasodilation and vasoconstriction are the first line defenses for thermia. So when there's hyperthermia, it's too hot, we do vasodilation first. Then we do sweating, or we constrict. When it's too cold, we constrict. Then we do shivering. But the first step is we do vasodilation or vasoconstriction. Now your book is really nice. That's why I really encourage you to read it. And what happens in the book is it explains to you what happens in the room, not even in your body. So you have a thermostat computer. The thermostat has a sensor. It detects that the room temperature fell to 19 degrees Celsius. Is that hyperthermia or hypothermia? Okay, so the room temperature fell down to 19 degrees Celsius. Fell down to 19 degrees Celsius. Is that hyper or hypo? So that's hypo. So if I want to replace that, do I need to do positive feedback, make it even more cold, or negative feedback, bring the temperature up? Negative feedback. So the thermostat activates the furnace, not the AC, because if you turn on the AC, that would be positive feedback. But we turn on the thermostat. The thermostat is going to turn on the furnace. The furnace is going to bring the temperature up. And then when we reach the healthy range, we got to stop. Otherwise, the temperature is going to keep going up until now we're going to go beyond homeostasis to hyperthermia. So now we went from hypothermia to hyperthermia, and only we needed euthermia. So we need to be able to stop, terminate the secretion of insulin when we reach euglycemia, terminate glucagon when we reach euglycemia, terminate shivering when we reach euglycemia, terminate sweating when we reach euglycemia. Yes?
A question that may not be related.
That's fine.
Why do they say like people take ice baths? Why is that good for you if it causes you to be like that hypothermic state?
Ice bath?
Yeah.
Ice bath is a form of, actually it's very healthy, the ice bath, especially if you have like a fever.
Yeah.
That is so true. One time I had a fever and I took like a cold shower. I promise you, like when I walked out, I felt like I was healthy. Before I was weak, I was I was shivering, I felt sick. So I turned on the cold shower, and then especially when I turned my back and the cold water hit me in the back, it was the most painful thing. But after a while, I felt like I don't feel like I'm sick anymore. It really works. So ice bath for what?
Do you think that that's like the, like athletes do it?
Athletes do it because that exercise is a form of inflammation. Did I talk about inflammation in the other lecture? So we talked about inflammation developing after necrosis, after cell injury, after acute inflammation. But what is it? It's a state of heat. It has five cardinal signs where there's heat, there is redness, there's pain, there's swelling, and all of that is because we're trying to. There's a big problem. So, for example, these athletes, they run a lot, so their joints are frictioning against each other. So there is a form. This friction causes stress or injury. So there is heat, there is redness, there is pain. So the negative feedback would be to put something cold to bring down this warm, this heat, to make it go away. So that's why they put the ice. But yeah, but I'm not saying like when they go and jump in the yeah, something like that. I heard about that. Yeah, there's like a North Pole cruise, and then they tell you like go and take a plunge into the North Pole. Yeah, I don't know. That's hypothermia. Okay, so that shows you this is a set point, 37 degrees Celsius. You see? Now the temperature, if it goes up to 37.5, that's an example of hyperthermia. So that's euthermia, that's hyperthermia. We replace the hyperthermia with vasodilation and then sweating. You see vasodilation and sweating. But when it drops down to 36.5, that's no longer euthermia. What is that? Hypothermia. So we replace that, the first step, by doing what? Vasoconstriction, and then the shivering, where we convert mechanical energy into chemical energy, ATP. Homeostasis. So that is an example of blood pressure when there is hypertension. So when there's hypotension, baroreceptor is one, hypotension. So when you wake up in the morning and you stand up, blood falls from your brain, from your head and neck. So there is a loss, a drop in the blood perfusion to your brain and your head and neck. So what happens is the rise from bed, the blood drains from the head, and the blood pressure falls in this region, and that is detected by the baroreceptors that transmit signals to the cardiac center of the brainstem. So now the cardiac center of the brainstem is the integrator. Remember, I told you there is a sensor. We begin with a sensor. So in this case, the sensor is the baroreceptor. They sense, because they are so close to the heart, they sense that there is a drop in the stretch of the aorta, in the stretch of the blood vessels close to the heart. So they are not stretched because there's not a lot of blood propelling against them. So what they do is they send a signal, integration signal, input signal to the brainstem, and the brainstem transmits signals to the heart, causing the heart to increase the heart rate, raising the blood pressure and restoring homeostasis. Okay, so the barrel reflex illustrates the common components of a feedback loop. So the receptor is the structure that that senses the change in the body. For example, the baroreceptors above the heart that monitor the blood pressure. Then the integrating. There's an integrating control center. That control center processes the sensory information and it makes a decision and directs the response, the cardiac center of the brain and the brainstem. And the effector here would be, who would be the effector in the baroreflex? The heart, because it was the one who responded to the brainstem effects of the motor, these motor effects to increase the heart rate. Okay, so that shows us right here a person rising from bed, and the blood drains from the upper body, creating homeostatic imbalance, and the baroreceptors above the heart respond to the drop in the blood pressure, and then the integrating center, the computer here, the baroreceptors send signals to the cardiac center of the brainstem, and then the brainstem send the output motor signal to the heart, and then the heartbeat accelerates in response to the cardiac center, and then the blood pressure rises to normal, and then homeostasis is restored. Positive feedback is a self-amplifying cycle. So we talked about that. That leads to a greater change in the same direction as opposed to the corrective action of the negative feedback. So the normal way of producing rapid changes. So examples would be childbirth. And also, I haven't talked to you about this, but another example would be blood clotting. So whenever you are injured and blood is leaking, so the platelets would aggregate. So if one platelet aggregates, other platelets aggregate as well. And that would cause like a band-aid to stop the loss of blood. Also hemoglobin. So what happens in hemoglobin is that when hemoglobin takes oxygen from the lung, the more oxygen it takes, the more the other oxygens are going to join. And when it goes to the tissue, the more oxygen it unloads, it facilitates for other oxygens to leave and in a positive feedback manner to leave the hemoglobin into the tissue that demands them. And the same thing with carbon dioxide. So now one carbon dioxide makes its way to the hemoglobin, the others will follow. So that's also another form of positive feedback. Okay? So it can sometimes be dangerous. So that's a vicious cycle of runaway fever. So for example, coma, I mean like patients that do not have a correction in their hyperglycemia or hypoglycemia. Then if there's no correction, then the automatic natural thing would be positive feedback because you have a drop in blood sugar. If you don't correct it, you're gonna have even more drop. It's not gonna stay there. It's gonna keep going, leading to positive feedback, leading to coma. So that's the example of the giving birth. What happens is the stimulus is the baby. He's the one who starts everything. The baby's head of the fetus pushes against the cervix. And the nerve impulses from the cervix are transmitted to the brain, and the brain stimulates the pituitary gland to secrete oxytocin, and oxytocin stimulates the uterine contraction and pushes the fetus toward the cervix. Okay, we talked about the gradients, and we said that a gradient is a separation. So there's a difference in the chemical concentration, the charge, the temperature, or the pressure. So we talked about how blood flows from an area of a high partial pressure to an area of a lower partial pressure. We even talked about how chemicals flow down their concentration gradient from an area where there's a lot of molecules to an area of there is less molecules. What powers that movement? What powers the movement of molecules from an area of a higher molecular concentration to an area of a lower molecular concentration? Kinetic energy. Excellent. 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 And I said that Ke kinetic energy equals half mv squared. Very good. You guys are good. Very good. Okay. The same thing with charged particles. They flow down concentration gradient from more electropositive to less electropositive, or from more electronegative to less electronegative. And heat flows down thermal gradient. So your brain, you have a fever, you put that cold pad So now the heat is gonna move from your hot brain that's suffering from fever into the cold into that cold pad. Or when you take a cold shower, then your hot body, all of the heat is gonna leave from your body into the cold water. So the movement in the opposite direction is up the gradient and requires spending metabolic energy. We talked about that in what type of transporter, that we said it works against the concentration gradient. It sends things uphill, not downhill. Things flow from when there's a lot to there's a little, and then they take from where little and send it against the gradient. Yeah, that's active. Passive is when you move. Passive is so passive, like a waterfall. It moves from where there's a lot to where there's little. But when you take little and throw it back against a lot, you have 700 people outside trying to come in. Three make it their way in, and you take the three and you push them against the 700. That's active. So what molecule does that? What enzyme does that? I mentioned it earlier. It uses ATP to do that job. Yeah, ATPase. What is it? Sodium potassium ATPase. It sends sodium. So you have a lot of potassium inside, a lot of sodium outside. So the natural movement is for sodium to come from outside the cell to the inside, and for potassium to move from inside the cell to the outside. The sodium potassium ATPase does the opposite. The little bit of potassium that went outside, she brings it back in. And the little bit of sodium that made its way in, she pushes it back against everybody else to ensure that there is no equilibrium, so that when the action potential comes, she is able to mediate that action potential. It is a movement in the opposite direction. So the movement in the opposite direction is up the gradient and requires spending metabolic energy. So that is down gradient movement. That's passive diffusion. And that's moving up the gradient. That is a form of passive or active? Active diffusion. Very good. Okay, so we talked about how many gradients so far. We talked first of all about the pressure gradient. So we move from an area of high pressure next to the heart, because that's the pump. When the ventricles contract, they pump the blood very hard. So the pressure will always be the highest right here, where my mouse is pointing. And then it's gonna leave to an area where there is low blood pressure. And then we talked about another type of gradient, and that is the concentration gradient, where there is a lot of glucose moving from where there's a lot of glucose to where there's a little bit. And then we talked about the electrochemical. So where there is a lot of positive charge, you see, are going to go where there is a little bit of positive charge. So that's not a concentration gradient. That is an electrical gradient. So that's the electrical gradient. And here you have a lot of negative charge. They're going to move inside or outside? Outside, because there's a lot blue negative inside. They're going to move outside. Then there is thermal gradient, where there is hot, where your body is very warm, and that's your skin, and that's the cool air. So the heat is going to move all of the warm blood out into the colder regions. Okay, so now the rest is just something that's very simple. This is telling you that, that the history of anatomical terminology, about 90% of our current medical terms come from Latin, Greek roots. Some structures are named after people. These are eponyms, and acronyms are pronounceable words formed from first letter or first few letters, like PET, positron emission. Okay, there are plural forms of anatomical terms, and there are adjectives. So this is just showing you the importance of spelling And the unity of form and function, that's where anatomy and physiology complement each other, and they cannot be divorced from each other. The cell theory states that all structure and function result from the activity of the cells, and the human body is a product of evolution. And the human structure can be viewed as a series of levels of complexity. And we talked about the gradients and the flow. So matter and energy tend to flow down gradients, and homeostasis. Yes. No, not in all of them, but you should be familiar with them. You'll be restricted to like what I'm going to send you in the study guide. That's what you got to focus on. That's what you're going to see the exam on. Okay, so you just we will see what we have to abide by what the syllabus says. So I will send you announcements of what the agenda for each week, so you can prepare accordingly. Just look forward to the study guide. Look look forward to the homework that will be published, and it will be due the night before class. Yeah. Okay, so that describes to you the CT scan and the MRI. This is the PET, the positron emission tomography scan. Okay, so this is just to show you. I think we have completed the concept. I'll see you next week where we're going to be talking about